What if the Big Bang wasn't the beginning of everything? For centuries, we've thought of it as the moment the universe burst into existence. But what if there's more to the story? What if the cosmos has a history that stretches back even further? A history we're only just beginning to uncover. This isn't just a question for scientists and philosophers. It's a mystery that challenges everything we think we know about reality. Today, we're diving into the enigmatic question of what happened before the Big Bang, and the theories that attempt to answer it are as fascinating as they are mind-bending. From timeless cycles to parallel universes, these ideas will push the boundaries of your imagination and leave you questioning the very nature of existence. So get ready to explore the unknown, because what we're about to uncover might just change the way you see the universe forever. Let's start with a theory that suggests the Big Bang wasn't a beginning at all, but a transition from something even more profound. Let's take a moment to revisit the foundation of modern cosmology, the Big Bang theory. At its core, this theory describes how the universe as we know it began as an infinitely dense and tiny point, often referred to as a singularity. Around 13.8 billion years ago, this singularity underwent a rapid expansion, setting the stage for the cosmos we see today. It's a bit like watching a balloon inflate, except the balloon is the universe, and the dots on its surface are galaxies, all moving away from each other as space itself stretches. This idea isn't just a scientific guess. It's supported by a wealth of evidence, from the cosmic microwave background radiation to the way galaxies are speeding apart. But while the Big Bang theory explains how the universe expanded, it doesn't tell us what came before. What existed in that moment before everything began? Was there a before at all? These questions take us to the edge of human understanding, where science, philosophy, and imagination collide. And that's where the real mystery begins. What does it even mean to ask what happened before the Big Bang? This seemingly simple question takes us straight into the heart of one of the most profound challenges in both science and philosophy. Time, as we understand it, is woven into the very fabric of our universe. But if the Big Bang marked the birth of not just matter and energy, but also time itself, then the idea of a before becomes deeply puzzling. How can there be a before when time, the very framework for such a concept, didn't yet exist? It's like trying to find a place north of the North Pole. Once you've reached the edge, the question loses its meaning. This paradox forces us to rethink our most basic assumptions about reality. Our brains are wired to think in terms of cause and effect, beginnings and endings, but those ideas might not apply when we're talking about the origins of the universe. It's a reminder that the tools we use to understand the everyday world, tools like time and space, might not be equipped to handle the extraordinary. Yet, this doesn't stop scientists and thinkers from exploring the possibilities. Some theories suggest that the Big Bang wasn't the absolute beginning, but rather a transition from some other state of existence. Perhaps our universe emerged from a previous one, or maybe it's part of a larger multiverse where the concept of before takes on a completely different meaning. These ideas stretch the boundaries of our understanding, inviting us to consider realities that might lie beyond the limits of our imagination. What's fascinating is how this question doesn't just challenge science, it challenges philosophy, even spirituality. It forces us to confront the limits of human comprehension and grapple with concepts that might forever remain out of reach. And yet, that's precisely what makes it so compelling. The mystery of what, if anything, came before the Big Bang isn't just a scientific puzzle. It's a window into the vast, uncharted territory of existence itself. So, while we may not have definitive answers, the journey of exploring this question is as enlightening as it is humbling. It reminds us that the universe is far stranger, far more complex, and far more beautiful than we can fully grasp. And sometimes the act of asking the question is just as important as finding the answer. What if the Big Bang wasn't the beginning of everything but just a single event in an unending cosmic dance? This is the core idea behind the cyclic universe theory, a fascinating perspective that challenges our understanding of time and existence. Instead of a single, explosive origin, this theory suggests that the universe undergoes endless cycles of expansion and contraction, like a cosmic heartbeat that never stops. In this view, the Big Bang wasn't a unique starting point, but one of many bangs in an eternal sequence. The cyclic universe theory offers a compelling way to sidestep the question of a beginning. If the universe has always existed in this cycle, there's no need to pinpoint an ultimate origin. It's a concept that feels both ancient and modern, echoing ideas found in some of the world's oldest philosophies while fitting into the framework of contemporary physics. This theory also raises fascinating questions about the nature of time. Does it move in a straight line, or is it more like a loop, endlessly repeating? Contrast this with other theories, like the idea of a single, unique Big Bang, which suggests a definitive starting point for everything we know. While that idea paints a dramatic picture of creation, the cyclic universe theory offers a more nuanced vision, one of continuity rather than a singular moment. It's a reminder that our universe might be far more complex and mysterious than we've yet imagined. So, as we ponder the nature of existence, could it be that the story of the cosmos isn't a one-time event but an eternal symphony of expansion and collapse? What if our universe isn't the only one out there? Enter the Multiverse Hypothesis, a mind-bending idea that suggests our cosmos is just one of countless others, each with its own unique beginning, its own Big Bang. Picture an infinite cosmic tapestry where universes bloom, expand, and fade like bubbles in an endless sea. It's a concept that challenges the very notion of a singular before, proposing instead that our universe might have emerged from a vast, interconnected landscape of other realities. This theory doesn't just push the boundaries of our understanding, it redefines them. Instead of searching for a singular moment before the Big Bang, the multiverse hypothesis suggests that our universe could be part of a much larger, more complex system. In this framework, what we think of as the beginning might just be one event among countless others, each unfolding in its own corner of this grand cosmic expanse. It's a humbling thought our entire existence might be just one tiny thread in an unimaginably vast fabric. But here's where it gets even more fascinating. If there are other universes out there, could they interact with ours? Could they influence the laws of physics, the constants that govern our reality? Some theories suggest that collisions or overlaps between universes could leave traces, cosmic fingerprints, that we might one day detect. Imagine the possibilities, evidence of another universe, another Big Bang, just beyond the edge of our own. It's a tantalizing idea, one that could reshape everything we think we know about existence. The multiverse hypothesis doesn't just answer the question of what happened before the Big Bang, it turns it on its head. Instead of a single, linear timeline, it offers a sprawling, interconnected web of beginnings and endings, each with its own story to tell. And while it may seem like science fiction, it's a theory grounded in rigorous scientific thought, one that continues to push the frontiers of cosmology. So, what do you think? Could our universe be just one of many? And if so, what might that mean for the nature of reality itself? Picture a vast, empty ocean, perfectly still and silent. Now imagine that beneath this calm surface, tiny ripples begin to form, almost imperceptible at first. These ripples, though small, carry the potential to grow into something monumental. This is a lot like the quantum vacuum, a state of space that seems empty but is actually teeming with activity. In the pre-Big Bang era, this vacuum wasn't just a void, it was a playground for quantum fluctuations. These are tiny, random changes in energy that pop in and out of existence, governed by the strange rules of quantum mechanics. Think of it like bubbles forming in a pot of boiling water. Each bubble represents a fluctuation, appearing unpredictably and vanishing just as quickly. But every so often, one of these bubbles doesn't just disappear, it expands. In the context of the pre-Big Bang universe, this expansion could have been the spark that ignited the Big Bang itself. What's truly fascinating is that these fluctuations aren't bound by the laws of classical physics. They exist in a quantum realm where particles can appear out of nowhere and energy can fluctuate without a clear cause. This quantum realm is a world where the familiar rules of reality no longer apply. Instead of smooth, predictable motion, everything is governed by probabilities and uncertainties. It's as if the universe, in its earliest moments, was a game of chance with quantum fluctuations rolling the dice. And one of those rolls, one tiny, seemingly insignificant fluctuation, could have set the stage for everything we see today. So, while we can't peer directly into the pre-Big Bang era, the clues left behind by quantum mechanics offer us a glimpse into a universe that defies our everyday understanding. It's a reminder that even the smallest things can have the biggest consequences, and that the birth of our universe might have been the result of a quantum whisper in the cosmic silence. What if everything we see, touch, and experience, the vastness of the cosmos, the complexity of life, even the fabric of space-time itself, is nothing more than a projection? This is the essence of the holographic principle, a groundbreaking idea that suggests our three-dimensional universe might be encoded on a two-dimensional surface. It's like the universe is a cosmic version of a hologram, where every detail, every star, every galaxy is etched onto a boundary we can't see. But how does this mind-bending concept connect to the mystery of what happened before the Big Bang? The holographic principle emerged from the study of black holes, where physicists discovered something astonishing. All the information about matter that falls into a black hole seems to be stored on its surface or event horizon rather than lost forever. This led to the radical idea that the entire universe might work the same way. Its information encoded on a boundary like a cosmic hard drive. If this is true, it could mean that the Big Bang wasn't the beginning of everything but rather a transformation, a moment when this encoded information unfolded into the universe we know today. Think of it like a movie stored on a flat DVD. The disc itself is two-dimensional, but when you play it, a rich, immersive three-dimensional world comes to life. Could the universe be something similar? If so, the pre-Big Bang state might not be a void or a singularity, but a vast, two-dimensional surface brimming with encoded potential. This idea challenges our most basic assumptions about reality, suggesting that the universe is far stranger and more interconnected than we ever imagined. The implications are staggering. What we perceive as a three-dimensional world might just be the tip of an infinite holographic iceberg. And if that's the case, what other secrets might be hidden in the code of the cosmos? So, what if our universe wasn't born from a single explosive event, but instead emerged from something far stranger, a collision between cosmic layers we can't even see? That's the heart of the brain collision theory. Picture this: our universe exists on a three-dimensional membrane, or brain, floating in a higher dimensional space. Think of it like sheets of paper drifting in the air, each one capable of moving, bending, and yes, crashing into one another. When two of these brains collide, the energy released could be so immense that it sparks the birth of an entirely new universe. Sound like science fiction, maybe, but this theory has taken root in the minds of physicists as a compelling alternative to the classic Big Bang narrative. Now, here's where it gets even more mind-bending. These brains aren't just floating in nothingness, they're part of a larger, hidden dimension we can't directly observe. It's like trying to explain the ocean to a fish that's never left its own little pond. We're confined to our three-dimensional world, but beyond it, there could be countless other dimensions, each with its own set of rules and possibilities. But why would brains collide in the first place? Imagine those sheets of paper again. But this time they're constantly shifting and vibrating, pulled by forces we can't fully comprehend. Over time, their paths might cross, leading to a collision that sends ripples of energy cascading through space and time. those ripples could be the very fabric of our universe, the matter, energy, and laws of physics we experience every day. So, what does this mean for our understanding of reality? If the brain collision theory holds, it suggests that our universe is just one of many, a single bubble in a vast cosmic foam. Other universes might exist on their own branes, each with its own unique set of conditions. And while we can't see these dimensions directly, their influence might be etched into the very fabric of space itself. But here's the real question: if there are dimensions beyond our perception, how could we ever detect them? Could there be subtle clues hidden in the cosmos waiting to be uncovered? Or are we forever limited by the confines of our three-dimensional existence? These are the mysteries that keep physicists up at night, and they're the very questions that make the brain collision theory so endlessly fascinating. Before the Big Bang, the universe's potential birth was shaped by forces we're still striving to understand. Among these, dark energy and dark matter stand out as key players. Dark matter, an invisible substance that doesn't interact with light but exerts gravitational pull, likely played a crucial role in the pre-Big Bang state. Think of it as the cosmic scaffold, a hidden framework that helped shape the early conditions of the universe. Without it, the distribution of matter and energy might have been chaotic, making the universe's eventual expansion far less orderly. Then there's dark energy, the mysterious force driving the universe's accelerating expansion today. While we often associate dark energy with the present, its influence might have roots in the moments before the Big Bang. Some theories suggest that dark energy could have been a stabilizing force, ensuring that the universe didn't collapse back on itself before it even had a chance to begin. Together, dark matter and dark energy could have created the perfect balance, dark matter pulling things together, dark energy pushing them apart, laying the groundwork for the universe's explosive birth. What's fascinating is how these forces continue to shape the cosmos. Dark matter's gravitational influence is still at work, holding galaxies together, while dark energy drives the universe's expansion at an ever-increasing rate. Understanding their roles in the pre-Big Bang state not only sheds light on the universe's origins, but also helps us unravel the mysteries of its ongoing evolution. These invisible forces remind us that the universe is far more complex than what we can see, and their story is still being written. What if the universe didn't have a clear starting point at all? Stephen Hawking's no-boundary proposal challenges our very understanding of beginnings by suggesting that the universe has no distinct edge or moment of creation. Instead, it imagines time and space as a smooth, closed surface like the surface of a sphere, where there's no singular before to point to. In this view, the Big Bang wasn't an explosive event emerging from nothingness, but rather a transition from one state to another, where time itself becomes warped and continuous. Hawking's idea reframes the way we think about the origins of the cosmos. Instead of a linear timeline stretching back to a single starting point, time becomes more like a loop, blending seamlessly into itself. This raises fascinating questions about the nature of reality. If there's no boundary to the universe, does that mean the concept of a beginning is just a human construct? And how does this square with other theories about what happened before the Big Bang? Some ideas suggest a cyclical universe, while others propose a multiverse bursting into existence. Hawking's no-boundary proposal adds another layer to this puzzle, offering a perspective that doesn't rely on a traditional starting point at all. As we explore these ideas, it's worth considering how they challenge our fundamental assumptions about time, space, and existence itself. Could the universe truly be without a boundary, existing in a state that defies our everyday understanding? And if so, what does that mean for the stories we tell about its origins? What if the Big Bang wasn't the beginning of everything, but just a moment in an endless cosmic dance? This is the heart of the Big Bounce theory, a fascinating idea that suggests our universe might be one in an infinite series of expansions and contractions. Instead of a singular, explosive start, this model imagines the Big Bang as the result of a previous universe collapsing in on itself, like a cosmic heartbeat. It's a cyclical universe where each bounce marks the transition from contraction to expansion, creating a new universe in the process. One of the most compelling aspects of the Big Bounce theory is how it sidesteps the singularity problem. In traditional Big Bang models, the universe is thought to have begun as an infinitely dense and hot point, a singularity where the laws of physics as we know them break down. The Big Bounce offers a way out of this conundrum by suggesting that the universe never actually reaches that point of infinite density. Instead, quantum effects could intervene, preventing total collapse and allowing the universe to rebound into a new phase of expansion. It's a solution that blends the strange world of quantum mechanics with the large-scale structure of the cosmos. Unlike theories that propose a one-time, unique origin for the universe, the Big Bounce paints a picture of eternity. There's no definitive beginning or end, just an endless cycle of universes. This idea resonates with some ancient philosophies, like those in Hinduism or Buddhism, which also envision time as cyclical rather than linear. It's a reminder that even our most cutting-edge scientific theories sometimes echo humanity's oldest questions about existence. Of course, the Big Bounce isn't without its challenges. While it's a compelling idea, it's still a theory, and we don't yet have the observational evidence to confirm it. Questions remain about what exactly happens during the bounce phase and how a collapsing universe could transition smoothly into a new one. But that's the beauty of cosmology. It's a field filled with mysteries that push the boundaries of our understanding. In contrast to the Big Bounce, other theories propose that the Big Bang was a singular event, a one-time explosion that set everything into motion. These models often focus on the idea of a finite universe with a definitive starting point, raising questions about what, if anything, came before. The debate between a cyclical universe and a single origin model is one of the most profound in cosmology, highlighting just how much we still have to learn about the cosmos. So, what exactly caused the universe to balloon in size faster than the speed of light just moments after the Big Bang? This phenomenon, known as cosmic inflation, is one of the most fascinating pieces of the puzzle when we try to understand the early universe. Imagine stretching a balloon. Every point on its surface moves away from every other point as it inflates. Cosmic inflation works similarly, but on a scale that's almost impossible to grasp. In a fraction of a second, the universe expanded exponentially, smoothing out irregularities and setting the stage for everything we see today. But inflation isn't just about explaining how the universe got so big so quickly. It might also hold clues about what came before the Big Bang. If the universe underwent such rapid expansion, what could have triggered it? Some theories suggest that inflation was driven by a mysterious field of energy, often called the inflaton field, which existed in a pre-Big Bang state. This field could have provided the push needed to kickstart the universe's explosive growth. While we don't yet have direct evidence of this field, its effects are written all over the cosmos, from the uniformity of the cosmic microwave background to the distribution of galaxies we observe today. The intriguing part is that inflation might not have been a one-time event. Some models propose that it could happen repeatedly, leading to the creation of multiple bubble universes within a larger multiverse. If this is true, then the Big Bang we're familiar with might just be one of many such events, each with its own unique starting conditions. This idea opens up a whole new realm of possibilities, suggesting that our universe could be part of a much larger, interconnected cosmic landscape. But if inflation was the catalyst for our universe's birth, what existed before it? What set this entire process in motion? The answers to these questions might lie at the very edge of our understanding, where physics meets the unknown. But what if our universe's birth wasn't a singular explosion, but something far more dramatic, a cosmic collision? Enter the Ekpyrotic Universe model, a theory that reimagines the Big Bang as the result of two parallel universes smashing into each other. This idea paints a vastly different picture from the traditional view, suggesting that our universe didn't emerge from nothingness, but from the energy of a massive, universe-shattering collision. Unlike the Cyclic model, which proposes an endless loop of universes expanding and contracting, the Ekpyrotic model focuses on a single, cataclysmic event. Here, our universe isn't part of an infinite cycle, but rather the aftermath of two universes colliding in a higher dimensional space. This collision wouldn't just create a universe, it would send ripples of energy and matter outward, eventually forming everything we see today: stars, galaxies, and even us. The implications of this theory are mind-bending. If true, it suggests that our universe isn't alone. It's one of many, possibly infinite, parallel universes existing in a vast, multidimensional landscape. These universes might be separated by dimensions we can't perceive, only interacting in rare, explosive moments like the one that sparked our own existence. This idea also raises fascinating questions. Could other universes collide again, creating new worlds? And if so, what might those universes look like? The Ekpyrotic model doesn't just challenge our understanding of the Big Bang. It opens the door to a universe of possibilities where the boundaries of reality are far more complex and interconnected than we ever imagined. Now, let's shift our focus to one of the most fascinating and mind-bending ideas in modern physics: string theory. At its core, string theory suggests that the fundamental building blocks of the universe aren't particles like electrons or quarks, but incredibly tiny, vibrating strings. These strings, oscillating at different frequencies, are thought to give rise to everything we see around us, from the smallest atoms to the vast galaxies. But what does this have to do with the Big Bang? String theory offers a potential window into what might have happened before the Big Bang. While traditional physics struggles to describe the singularity, the point where all matter and energy were compressed into an infinitely dense state, string theory provides a different picture. Instead of a singularity, it proposes that the universe could have emerged from a state where these tiny strings interacted in a dense, high-energy environment. This opens up the possibility that the Big Bang wasn't the absolute beginning, but rather a transition from a previous state of the cosmos. One of the most intriguing aspects of string theory is its ability to reconcile quantum mechanics and general relativity, two frameworks that have long seemed incompatible. By describing the universe in terms of vibrating strings, it provides a unified framework that could explain the behavior of both the very small and the very large. However, string theory isn't without its challenges. For one, it requires extra dimensions up to 10 or 11 beyond the 3 spatial dimensions we're familiar with. While this might sound like science fiction, these hidden dimensions could hold the key to understanding the pre-Big Bang universe. So, how does string theory fit with other cosmological models? Some scientists see it as a complementary piece of the puzzle, while others argue it needs further evidence to be fully accepted. It's a theory that continues to spark debate and curiosity, pushing the boundaries of what we think we know about the cosmos. Could it be the key to unlocking the mysteries of the universe's origins? Only time, and perhaps more research, will tell. What if the very fabric of reality as we know it ceased to exist? That's the mind-bending question at the heart of the concept of a quantum singularity. In this mysterious state, the familiar laws of physics, gravity, time, space essentially break down, leaving us with a realm where our current understanding just doesn't apply. It's like trying to describe a color that no one has ever seen, or a sound that's never been heard. In the context of the pre-Big Bang universe, this idea becomes even more intriguing. Could a quantum singularity have been the crucible from which everything we know emerged? The challenge here is that studying these extreme conditions is like trying to piece together a puzzle with missing pieces. Our tools and theories, as advanced as they are, struggle to make sense of a place where time and space lose their meaning. Think of it this way: If the universe is a story, a quantum singularity is the blank page before the first word was ever written. We can't observe it directly, and our mathematical models hit their limits when faced with such extremes, but that doesn't mean we're completely in the dark. Scientists have turned to quantum mechanics and theoretical frameworks like string theory to try to peek behind this cosmic curtain. These approaches offer glimpses into how matter and energy might behave under such incomprehensible conditions. Yet, even with these tools, the quantum singularity remains one of the most elusive mysteries in cosmology. It's a reminder that, for all we've learned about the universe, there are still questions that push the boundaries of our knowledge, questions that might forever change how we see the cosmos. Entropy is often described as the measure of disorder in a system, but it's far more than that. It's one of the fundamental forces shaping the very fabric of our universe. To understand its role before the Big Bang, we need to think about what entropy might have looked like in that mysterious pre-expansion state. Some theories suggest that the universe began in a state of maximum entropy, a kind of cosmic equilibrium where energy was evenly distributed, and there was no room for change or complexity. But if that's the case, how did we get from that uniform, static state to the vibrant, dynamic universe we see today? One intriguing idea is that entropy didn't just emerge with the Big Bang, it might have been a driving force behind it. If the pre-Big Bang state was a soup of potential energy, entropy could have acted as the catalyst that tipped the scales, pushing the universe toward expansion. As it began to inflate, entropy would have increased, creating the conditions for matter, stars, and galaxies to form. It's almost as if entropy was the invisible architect, laying the groundwork for the cosmos to evolve into its current state of complexity. This raises another fascinating question. How does entropy continue to shape the universe's evolution? From the birth of stars to the eventual heat death of the cosmos, entropy is the force that governs the arrow of time, ensuring that systems move from order to disorder. It's why a shattered glass doesn't reassemble itself, and why the universe, over billions of years, moves toward a state of maximum entropy. But could there have been exceptions to this rule in the pre-Big Bang era? Could entropy have behaved differently in that primordial state, setting the stage for the universe we know today? By exploring entropy's role, we're not just uncovering clues about the universe's origins, we're also gaining insight into its ultimate fate. Whether it's the chaotic swirl of a galaxy or the slow decay of a star, entropy is there, quietly shaping the cosmos at every stage. It's a reminder that even in the earliest moments of existence, the universe was governed by forces that continue to define its journey through time. What if the universe we know, the vast expanse of stars, galaxies, and cosmic mysteries, was born not from a singular point, but from something even stranger, a two-dimensional surface? This is the essence of the holographic Big Bang theory, a radical idea that reimagines the very fabric of reality. Imagine the universe as a hologram where all the information we perceive in 3 dimensions is actually encoded on a flat, two-dimensional boundary. It's a concept that turns our understanding of space and time on its head, suggesting that the cosmos we inhabit might be nothing more than a projection from this underlying surface. So, how does this work? In this framework, the Big Bang wasn't the explosion of a tiny, dense point in a 3-dimensional space, but rather the emergence of our universe from a 2-dimensional plane. Think of it like a movie screen. Everything we see is playing out in 3 dimensions, but the source of that story exists on a flat surface. This idea builds on the holographic principle, which proposes that the information needed to describe everything in a volume of space can be encoded on its boundary, much like how a hologram stores a 3-dimensional image on a 2-dimensional surface. But why does this matter? For one, it challenges our traditional notions of space and time. If the universe is a hologram, then space isn't fundamental, it's an emergent property, something that arises from simpler underlying structures. Time, too, might not be what we think it is. In this view, the flow of time could be an illusion, a side effect of the way information is processed and projected from the two-dimensional surface. It's a perspective that forces us to rethink not just the Big Bang, but the very nature of reality itself. The implications are profound. If the holographic Big Bang theory holds, it could unify some of the biggest puzzles in physics, like the relationship between quantum mechanics and gravity. It might even provide clues about what, if anything, existed before the Big Bang. Could the two-dimensional surface be a remnant of a previous universe, or perhaps a bridge to other dimensions? These are questions that push the boundaries of our understanding, inviting us to explore the universe in ways we've never imagined. What does this mean for us? It's a reminder that reality might be far stranger and more complex than we've ever thought. The holographic Big Bang theory isn't just a scientific idea. It's a window into a deeper, more interconnected cosmos, one where the lines between dimensions blur and the nature of existence itself becomes a question worth asking. What if the birth of our universe was not an isolated event, but the result of something far more mysterious? Enter black holes, cosmic phenomena so dense that not even light can escape their gravitational pull. But could these enigmatic objects be more than just destructive forces? Some theorists propose that black holes might actually be the gateways to understanding what happened before the Big Bang. Imagine for a moment that our universe is like a bubble within a much larger cosmos. In this scenario, a black hole in another universe could have collapsed, triggering a singularity, a point of infinite density, that then expanded into the Big Bang, giving rise to everything we know today. This idea, often called the black hole cosmology, suggests that universes could be nested within one another like Russian dolls, with black holes serving as the bridges between them. While this might sound like science fiction, it's a theory grounded in the mathematics of general relativity and quantum mechanics. Black holes, long thought to be the end of existence, might instead be the spark that ignites new universes. So, could the key to unraveling the origins of our cosmos lie in the heart of these cosmic behemoths? It's a question that challenges our understanding of space, time, and reality itself, inviting us to rethink the very nature of existence. What if the very fabric of time, the ticking clock that governs our lives, didn't exist before the Big Bang? It's a mind-bending idea that challenges everything we think we know about cause and effect. We're used to thinking of time as a straight line, with events unfolding one after another. But what if that line didn't start until the Big Bang? This raises profound questions. Can there be a before if there's no time to measure it? And if time began with the universe, how do we even begin to make sense of what might have existed without it? This concept isn't just philosophical, it's rooted in some of the most cutting-edge theories in physics. One leading idea is that time, as we experience it, is a product of the universe's expansion. Before the Big Bang, the rules might have been entirely different. Some scientists suggest that time could have been intertwined with space in a way we can't yet comprehend, or that it might have operated on a fundamentally different scale if it existed at all. This doesn't just challenge our understanding of time, it reshapes our entire framework of causality, the idea that one event leads to another. Without time, can there be cause and effect? Or does causality itself break down in the absence of a temporal structure? Interestingly, this isn't just speculation. Theories like loop quantum gravity and string theory propose alternative frameworks for understanding time, or the lack of it before the Big Bang. For instance, loop quantum gravity suggests that time might emerge from the quantum fabric of space-time, rather than being a fundamental feature. String theory, on the other hand, hints at higher dimensions where time behaves in ways we can't yet imagine. These ideas don't give us definitive answers, but they open the door to possibilities that stretch beyond our current understanding of reality. What's truly fascinating is how these theories push us to rethink not just time, but the very nature of existence. If time didn't exist before the Big Bang, then the universe's origin might not be a single event in time, but something entirely outside of it. It's a concept that feels almost impossible to grasp, yet it's one of the most intriguing questions in modern cosmology. As we explore these ideas, we're not just learning about the universe, we're also learning about the limits of our own understanding and the endless possibilities that lie beyond. Quantum gravity stands as one of the most profound challenges in modern physics, a puzzle that scientists have pursued for decades. It's the attempt to bridge two of the most successful yet seemingly incompatible theories, quantum mechanics, which governs the tiny world of particles, and general relativity, which describes the vast cosmos. Together, they paint a picture of the universe's behavior at both the smallest and largest scales. But what happens when these two frameworks collide? This is where quantum gravity steps in, offering a potential key to unlocking the mysteries of the pre-Big Bang era. One of the central ideas in quantum gravity is that space and time might not be smooth and continuous, as Einstein's theory suggests, but rather granular and quantized at the tiniest scales. Think of it like zooming in on a digital image. Eventually, you'll see the individual pixels. Similarly, at the Planck scale, space-time itself might break down into discrete units. This radical shift in our understanding of the fabric of reality could help explain what might have existed before the Big Bang. Instead of a singularity, a point of infinite density, quantum gravity suggests a quantum foam, a seething, fluctuating state where space and time are constantly being created and destroyed. The implications are staggering. If quantum gravity can reconcile the laws of the very small with the laws of the very large, it might reveal a universe that cycles through periods of expansion and contraction, or even one where the Big Bang wasn't the absolute beginning but rather a transition from a previous state. This theory could fundamentally alter our understanding of cosmology, turning the Big Bang from a singular event into just one chapter in a much larger cosmic story. But how close are we to solving this puzzle? While progress has been made, quantum gravity remains a work in progress. Theories like loop quantum gravity and string theory propose different approaches, each with its own strengths and challenges. Loop quantum gravity, for instance, suggests that space is woven from tiny loops, while string theory envisions the fundamental units of reality as vibrating strings. Both aim to describe the universe in a way that encompasses both quantum mechanics and general relativity, but neither has yet provided a complete picture. What's clear, though, is that quantum gravity isn't just an academic exercise. It's a quest to redefine our understanding of the cosmos, potentially offering insights into the very nature of time, space, and existence itself. If successful, it could revolutionize not just cosmology but our entire perspective on reality. Could it be that the Big Bang was not the beginning but a moment of transformation? And if so, what does that mean for the story of the universe? These are the questions that quantum gravity seeks to answer, inviting us to rethink everything we thought we knew about the cosmos. What if everything we perceive as reality, the stars, the planets, even the very fabric of space-time, is nothing more than an elaborate simulation? This is the core idea behind the simulation hypothesis, a theory that has gained traction among scientists and philosophers alike. The concept suggests that our universe could be an incredibly advanced computer program created by a higher intelligence. If true, this might offer a fascinating explanation for the pre-Big Bang state. Instead of a traditional beginning, our universe could simply be the result of code being executed, a virtual environment booting up from some sort of cosmic hard drive. But how does this connect to the Big Bang? Think of it like starting up a video game. Before the game begins, there's a loading screen, a moment where nothing seems to exist yet, but everything is being prepared behind the scenes. In this analogy, the Big Bang could be the moment the simulation officially starts, and whatever existed before it might just be the equivalent of the code being written, the rules being set, or the program being initialized. It's a radical idea, but one that ties neatly into modern advancements in computing and artificial intelligence. Of course, this hypothesis isn't without its philosophical challenges. If we are living in a simulation, who or what is the programmer? Are we merely characters in someone else's game, or is there a deeper purpose to our existence? These questions push us to rethink not just the origins of the universe, but the very nature of reality itself. The simulation hypothesis forces us to confront the possibility that everything we know, every law of physics, every historical event, every moment of our lives, could be the product of a meticulously crafted code. And if that's the case, it opens up a whole new frontier of questions about free will, consciousness, and the ultimate meaning of existence. So, as we ponder the simulation hypothesis, we're not just exploring a scientific theory, we're stepping into a realm where science, philosophy, and even spirituality intersect. It's a thought-provoking reminder that the mysteries of the universe might be far stranger than we've ever imagined. What if consciousness isn't just a byproduct of the universe, but one of its essential building blocks? This idea might sound like something out of science fiction, but some physicists and philosophers argue that consciousness could be as fundamental as space, time, and matter. In fact, certain theories suggest that consciousness might have played a role even before the Big Bang. This concept, often called panpsychism, proposes that consciousness is a universal property, something woven into the very fabric of existence. Think of it this way: just as gravity is a force that permeates the cosmos, consciousness could be an intrinsic feature of reality itself. But how does this connect to the pre-Big Bang state? If consciousness is fundamental, it might have existed in some form even in the absence of the universe as we know it. Some thinkers speculate that the pre-Big Bang state wasn't purely physical, but perhaps a realm where consciousness and potentiality intertwined. This raises a fascinating question. Does consciousness shape our perception of reality, or is it the other way around? Could our understanding of the universe be limited by the nature of our own awareness? As we explore these ideas, we're not just pondering the origins of the cosmos. We're also examining the very nature of our existence and how we fit into the grand cosmic puzzle. Before the Big Bang, the universe wasn't just an empty void. It was a seething, chaotic sea of particles and energy, often referred to as a primordial soup. Picture a cosmic pot simmering with the fundamental ingredients of everything we know today: quarks, electrons, photons, and more, all jostling in a high-energy frenzy. This dense, hot mixture wasn't random. It was the starting point for everything that followed, the raw material of existence itself. But how did this chaotic soup transform into the structured universe we see now? That's where the idea of symmetry breaking comes into play. Symmetry breaking is a bit like shaking a snow globe. Initially, everything inside is evenly distributed, but when you shake it, the flakes settle into new patterns. In the primordial soup, the universe's fundamental forces, gravity, electromagnetism, the strong force, and the weak force, were unified, perfectly symmetrical. But as the universe began to expand and cool, this symmetry started to break, like a cosmic snow globe settling into place. Forces separated, particles gained distinct identities, and the universe took its first steps toward becoming the complex, structured cosmos we know today. This process wasn't just a random event, it was a critical turning point. Without symmetry breaking, particles might have remained locked in that chaotic soup, never forming atoms, stars, or galaxies. It's a reminder that even in the universe's earliest moments, small changes had monumental consequences. So when we look up at the night sky, we're not just seeing stars, we're seeing the echoes of that primordial soup and the delicate balance that made it all possible. So, what could have caused the universe to shift from that initial, perfectly balanced state into the complex, diverse cosmos we see today? The answer might lie in something called symmetry breaking. Think of it this way: imagine a pencil standing perfectly upright on its tip. It's symmetrical, equally balanced in every direction. but the slightest nudge causes it to fall, breaking that symmetry and choosing a specific direction. In the early universe, something similar could have happened, but on a cosmic scale. Symmetry breaking is the process by which the universe's initial, highly symmetrical state was disrupted, leading to the emergence of distinct forces, particles, and structures. In the pre-Big Bang era, the universe might have been in a state of perfect symmetry, where all fundamental forces were unified into a single, undifferentiated entity. But as it cooled and expanded, this symmetry broke apart, giving rise to the four fundamental forces we know today: gravity, electromagnetism, and the strong and weak nuclear forces. This process didn't just create the forces that govern our universe, it also set the stage for the formation of matter itself. Particles like quarks and electrons emerged from the broken symmetry, eventually combining to form atoms, stars, and galaxies. Without symmetry breaking, the universe might have remained a featureless, homogeneous void, devoid of the complexity and diversity we observe. But here's a fascinating question: what triggered this symmetry breaking in the first place? Some theories suggest that quantum fluctuations, tiny, random variations in energy, played a crucial role. These fluctuations, magnified by the rapid expansion of the universe, could have pushed the system out of its symmetrical state, creating the nudge that led to the cosmos we know. The implications of symmetry breaking go even deeper. It's thought to have influenced the distribution of matter and the formation of large-scale structures in the universe. Regions with slightly higher density caused by these early fluctuations became the seeds for galaxies and galaxy clusters. In a way, symmetry breaking didn't just shape the universe, it gave it a blueprint for growth. So, as we reflect on the pre-Big Bang era, symmetry breaking offers a compelling explanation for how a simple, symmetrical state could evolve into the rich, intricate cosmos we inhabit. It's a reminder that even in the most fundamental processes of the universe, there's a delicate dance between order and chaos, symmetry and diversity. Imagine a universe where space and time are not smooth and continuous, but instead resemble a bubbling, frothy ocean, constantly churning with tiny, fleeting particles. This is the concept of quantum foam, a theoretical framework that suggests the very fabric of space-time might not be as orderly as we once thought. At the tiniest scales, space could be a chaotic sea of virtual particles popping in and out of existence, defying our traditional notions of reality. But here's the intriguing part. Some scientists propose that this quantum foam might have been the precursor to the Big Bang itself, a seething, unstable foundation from which our universe emerged. This idea turns our understanding of space and time on its head. Instead of a calm, predictable backdrop, space-time becomes dynamic, unpredictable, and fundamentally unstable at its core. It's a concept that stretches the limits of our imagination and challenges the very tools we use to study the cosmos. And while quantum foam is still a theoretical construct, something we can't yet observe directly, it opens up profound questions about the nature of existence. How did something so chaotic give rise to the structured universe we see today? What does this mean for the laws of physics as we know them? The implications for cosmology are staggering. If quantum foam existed before the Big Bang, it suggests that our universe might have arisen from a fundamentally different kind of reality, one where the rules we take for granted, like cause and effect, might not have applied. It forces us to reconsider not just the origins of the cosmos, but also the very framework we use to understand it. Could this chaotic, frothy state hold the key to unlocking the mysteries of the universe's birth? As we continue to explore this idea, one thing becomes clear. The quantum foam concept reminds us that the universe is far stranger and more fascinating than we've yet imagined. So, what if the nothingness before the Big Bang wasn't actually nothing at all? Enter vacuum energy, a fascinating concept that challenges our understanding of empty space. Vacuum energy is the energy that exists in what we perceive as a void, a subtle but powerful force inherent to the fabric of the universe. Even in the absence of matter, space isn't truly empty. It's teeming with this latent energy. Scientists theorize that vacuum energy could have played a pivotal role in the moments leading up to the Big Bang, providing the spark that set everything into motion. Here's where it gets even more intriguing. Vacuum energy is deeply tied to the idea of cosmic inflation, the rapid expansion of the universe in its earliest moments. During this phase, vacuum energy acted like a cosmic engine, driving the universe to stretch exponentially in a fraction of a second. This process not only explains how the universe grew so vast so quickly, but also why it appears so uniform on large scales. It's like blowing up a balloon. The surface stretches, smoothing out any irregularities. But the story doesn't end there. Vacuum energy isn't just a relic of the past, it continues to shape the cosmos today. In fact, it's thought to be the driving force behind the accelerated expansion of the universe, a phenomenon we attribute to dark energy. So, the same energy that might have ignited the Big Bang is still at work, pushing galaxies apart and sculpting the future of the universe. What does this mean for our understanding of reality? Could vacuum energy hold the key to unraveling the deepest mysteries of existence? The answers might just lie in the very fabric of the void. What if the Big Bang wasn't the ultimate starting point, but just one chapter in a much larger story? This is the fascinating idea behind the concept of a pre-Big Bang universe. Some theories propose that before the Big Bang, an entirely different universe existed, governed by its own unique laws of physics. Imagine a cosmos where the rules we take for granted, like gravity or the speed of light, might not have applied. This concept shakes the foundation of our understanding, challenging the idea that the Big Bang was the singular beginning of everything. It suggests instead that our universe might have emerged from a previous state, one that could have been entirely unrecognizable to us. But how could such a universe even exist? One intriguing possibility is a process called a cosmic bounce. Picture a universe that collapses in on itself, reaching a point of extreme density before rebounding outward in what we now call the Big Bang. This idea implies that the universe could be cyclical, expanding and contracting over time, with each cycle ushering in a new era of existence. It's a theory that opens the door to an infinite series of universes, each with its own distinct characteristics. This leads us to an even grander idea, the multiverse. If a pre-Big Bang universe existed, could there be countless others out there, each with its own Big Bang moment? The multiverse theory suggests that our universe is just one of many, like a single bubble in a vast cosmic foam. Each bubble universe could have its own set of physical laws, giving rise to realities that might be wildly different from our own. This concept not only challenges our understanding of the Big Bang, but also invites us to rethink the very nature of existence. As we explore these theories, one thing becomes clear: the Big Bang may not be the definitive starting point we once thought it was. Instead, it could be part of a much larger, more complex tapestry of universes, each with its own story to tell. And if that's the case, the mysteries of the cosmos are far deeper and far more fascinating than we ever imagined. When we think about the moments before the Big Bang, we're venturing into a realm where observation and experimentation hit their limits. This is where mathematical models step in, acting as a bridge between the unknown and the knowable. These models are not just equations on a page, they're tools that allow scientists to simulate conditions that are otherwise impossible to recreate. By applying principles from quantum mechanics, general relativity, and even string theory, researchers can explore potential scenarios for the pre-Big Bang universe. But here's the catch: while these models can paint fascinating pictures, they're only as good as the assumptions and data that feed into them. One of the biggest challenges lies in testing these theories. After all, how do you verify something that happened before time and space as we know them even existed? This is where the gap between theory and observation becomes stark. Mathematical models can suggest that the universe might have started as a quantum fluctuation or emerged from a collision of higher dimensional branes, but without observable evidence, these ideas remain in the realm of speculation. It's a bit like trying to reconstruct the life of a person by only knowing their shadow. There's a lot of guesswork involved, so how does science navigate this uncertainty? One approach is to look for indirect evidence. For example, if a model predicts certain patterns in the cosmic microwave background, the faint afterglow of the Big Bang scientists can search for those signatures. Another strategy is to refine these models by aligning them with what we do know about physics, gradually narrowing down the possibilities. While we may never directly observe the pre-Big Bang state, the process of testing and refining these models brings us closer to understanding the origins of everything. The question remains, can we ever truly bridge the gap between theory and observation, or will the pre-Big Bang universe always remain just out of reach? What if the Big Bang wasn't the absolute beginning but rather a dramatic leap from something that came before? Enter the concept of a quantum tunnel, a mind-bending idea rooted in the world of quantum mechanics that could reshape how we think about the origins of the universe. At its core, a quantum tunnel describes how particles can suddenly appear in places they seemingly shouldn't be able to reach, bypassing the usual rules of physics. It's as if they've found a hidden passage through what should be an impenetrable barrier. Now, imagine applying this idea on a cosmic scale. Instead of particles, what if it was the entire universe that emerged through a quantum tunnel? This theory suggests that our universe might have transitioned from a pre-existing state, some kind of quantum realm, into the expanding cosmos we see today. This concept ties directly to quantum mechanics, where uncertainty and probability reign supreme. In the quantum world, particles don't follow the predictable paths we're used to in classical physics. Instead, they can appear, disappear, or even tunnel through barriers in ways that seem impossible. If the universe itself operates under these same quantum principles, it's not far-fetched to think that it, too, could have tunneled into existence from an earlier state. But what does this mean for cosmology? If true, it could challenge our understanding of the Big Bang as a singular starting point. Instead, it might represent a moment of transition, a cosmic leap from one state of existence to another. This idea opens up fascinating questions. Was there a universe before ours? And if so, what kind of quantum processes could have driven such a monumental shift? Exploring this theory isn't just about rewriting the history of the cosmos, it's about rethinking the very nature of existence. Could the universe be part of a larger quantum-driven cycle, constantly transitioning from one form to another? While this idea is still speculative, it's a powerful reminder of how quantum mechanics continues to challenge our understanding of reality on both the smallest and largest scales. What if the very fabric of our universe is built not just on matter and energy, but on something far more fundamental: information? This is where information theory steps in, a field that examines how information is processed, stored, and transmitted. It might seem like an abstract concept, but when applied to the cosmos, it could hold the key to understanding what happened before the Big Bang. At its core, information theory suggests that everything in the universe, from particles to galaxies, can be described in terms of information. Think of it like this: a book isn't just paper and ink, it's the information encoded in those words that gives it meaning. In the same way, the universe might be a vast, intricate code, with every event and object representing a piece of data. But how does this tie into the pre-Big Bang state? One intriguing idea is the holographic principle, which proposes that all the information in a three-dimensional space like our universe can be represented on a two-dimensional surface. Imagine the entire cosmos as a hologram, where what we perceive as three-dimensional reality is actually encoded on a flat boundary. If this principle holds true, it could mean that the pre-Big Bang state wasn't a chaotic mess, but a highly organized flow of information waiting to unfold into the universe we know today. But here's where it gets even more fascinating. If information shapes the universe, could it also define its origins? What if the Big Bang wasn't just a burst of energy, but the moment when a specific set of informational parameters were activated, setting the stage for everything that followed? This shifts our perspective, turning the question of what happened before into what was the informational blueprint that created it. As we dive deeper into these theories, one thing becomes clear: the universe might be far more than the sum of its physical parts. It could be a dynamic, information-driven system with its origins rooted in the very nature of how information operates. So, what does this mean for our understanding of existence? How does the way information flows and interacts shape not just the universe but reality itself? What if time, as we know it, isn't the linear, flowing river we imagine it to be? Some theories suggest the universe itself might be timeless, existing without a clear beginning or end. This radical idea challenges one of the most fundamental aspects of our existence: our understanding of time as a sequence of past, present, and future. In a timeless universe, events don't happen in a straight line but might exist all at once, like frames in a film reel. Think of it this way: instead of watching a movie scene by scene, you're seeing the entire story laid out before you, every moment simultaneously present. This notion isn't just a scientific curiosity, it reshapes how we think about reality itself. The idea of a timeless cosmos forces us to reconsider what it means for something to happen or exist. If time isn't a linear progression, then the Big Bang might not be a singular event marking the start of everything, but rather a point in a much larger, more complex framework. Some physicists argue that time is an emergent property, something that arises from the interactions of particles and forces rather than being a fundamental feature of the universe. This means time could be more like an illusion, a way our brains make sense of the world rather than an absolute truth. Philosophically, a timeless universe raises profound questions about our place in the cosmos. If there's no beginning or end, what does that mean for concepts like purpose, destiny, or even free will? Are we simply parts of an eternal, unchanging whole, or do our choices still carve out meaning in a reality where time doesn't flow? These questions don't just belong to scientists, they invite all of us to rethink what it means to live in a universe that might not play by the rules we've always assumed. As we grapple with these ideas, we're not just exploring the cosmos, we're exploring the very nature of existence itself. Now, let's shift our focus to a fascinating and somewhat mind-bending concept: cosmic strings. These hypothetical one-dimensional defects in space-time are thought to have formed during the earliest moments of the universe, long before the Big Bang as we know it. Imagine them as incredibly thin, almost unimaginably long threads stretched across the cosmos, remnants of a phase transition in the very fabric of reality. But why are they so important? Cosmic strings could hold the key to understanding the structure of the universe itself. These strings, if they exist, would carry immense energy and warp the space-time around them, creating ripples that could influence the distribution of matter and energy in the universe. They might even act as cosmic seeds, around which galaxies and galaxy clusters eventually formed. By studying their potential effects, scientists aim to uncover clues about the conditions of the pre-Big Bang universe. Could cosmic strings explain why the universe looks the way it does today? The answer to that question might lie in the intricate dance of these elusive structures. But here's the real challenge: how do we detect something so strange and so subtle? Cosmic strings, if they're out there, are incredibly difficult to spot. They don't emit light or other easily detectable signals. Instead, researchers look for their gravitational effects, such as tiny distortions in the background radiation of the universe or the way they might bend light from distant stars. The search for cosmic strings is a bit like trying to find a needle in a haystack, but one that could reshape our understanding of the cosmos. What would it mean if we finally found evidence of these cosmic threads? The implications could be nothing short of revolutionary. So, what if I told you that empty space isn't really empty at all? Welcome to the strange and fascinating world of the quantum vacuum. In the realm of quantum physics, even the void is alive with activity. The quantum vacuum is often described as the lowest possible energy state in the universe, a sea of empty space teeming with fleeting particles and energy fluctuations. These aren't just random blips, they're governed by the laws of quantum mechanics, where particles pop in and out of existence in a fraction of a second. It's like an invisible, ever-churning ocean beneath the surface of reality. Now, how does this relate to the Big Bang? Think of the quantum vacuum as a potential starting point, a cosmic canvas where the seeds of our universe could have first appeared. Some theories suggest that the Big Bang itself might have emerged from this quantum soup, a sudden burst of energy that set everything into motion. If that's the case, the quantum vacuum could be the backdrop for the most dramatic event in cosmic history. It's a reminder that even nothingness holds the potential for something extraordinary. But what does this mean for our understanding of the universe's origin? If the quantum vacuum played a role, it challenges the idea that the Big Bang was the absolute beginning. Instead, it opens the door to possibilities like a cyclical universe or even a multiverse where the vacuum acts as a bridge between different cosmic events. It's a concept that pushes the boundaries of our imagination, inviting us to rethink what we know about time, space, and existence. So, how do scientists even begin to tackle the question of what happened before the Big Bang? One of the biggest challenges lies in finding observational evidence. Since the Big Bang marks the beginning of space-time as we know it, peering beyond it requires entirely new ways of thinking and innovative tools. It's like trying to read a book when the first page has been torn out. You need to piece together clues from what's left. One promising approach involves studying the cosmic microwave background, or CMB, which is essentially the oldest light in the universe. While the CMB tells us a lot about the moments immediately after the Big Bang, some scientists believe it might also hold faint traces of what came before. Think of it as an echo, a subtle whisper from the universe's earliest moments. Researchers are developing advanced technologies like next-generation telescopes and quantum sensors to detect these elusive signals. Another avenue is the study of gravitational waves, ripples in space-time caused by massive cosmic events. These waves could carry information from epochs even earlier than the Big Bang, offering a potential window into the pre-Big Bang universe. Projects like the Laser Interferometer Space Antenna, or LISA, aim to detect these waves with unprecedented precision, opening up entirely new possibilities for exploration. But here's the thing, even with these cutting-edge tools, the search for pre-Big Bang evidence is incredibly complex. The universe's expansion has stretched and distorted any traces that might have existed, making them nearly impossible to detect. It's a bit like trying to recognize a photograph that's been crumpled, faded, and torn apart. Scientists are also exploring theoretical frameworks like loop quantum gravity and string theory to help interpret what these faint signals might mean. What's truly exciting is how future discoveries could completely reshape our understanding of the cosmos. Could we one day find definitive proof of a universe that existed before ours? Or will the mysteries of the Big Bang remain forever out of reach? These questions push the boundaries of science, reminding us just how much there is still to learn. Every new observation, every breakthrough, brings us a little closer to uncovering the story of our universe's beginnings and perhaps its ultimate origins. One of the most profound aspects of pre-Big Bang theories isn't just the science, it's the way they force us to confront questions that stretch far beyond the boundaries of physics. What does it mean for something to exist before existence itself? And how do we, as finite beings, even begin to grapple with concepts that might lie outside the limits of human understanding? These are the kinds of philosophical puzzles that these theories bring to the surface, challenging not just what we know, but how we think about knowing itself. At the heart of this exploration is the very nature of existence. If the Big Bang marked the beginning of our universe as we know it, what could have preceded it? Was it nothingness, or something so fundamentally different that our language and logic struggle to describe it? Philosophers have long debated the nature of being, but pre-Big Bang theories push these questions into uncharted territory. They invite us to consider whether existence itself might have layers or dimensions we can't yet fathom. These ideas also shine a light on the limits of human knowledge. We're used to studying the universe from within its framework, but pre-Big Bang theories ask us to step outside that framework, or at least try to. Can our minds, shaped by the rules of this universe, truly comprehend what might lie beyond it? This isn't just a scientific challenge, it's a philosophical one. It forces us to confront the humbling reality that there may be truths forever beyond our grasp. But rather than leaving us feeling defeated, these questions can be a source of wonder. They remind us that curiosity is at the core of what it means to be human. Even if we can't fully answer these mysteries, the act of asking them expands our perspective, pushing the boundaries of how we see ourselves and our place in the cosmos. Pre-Big Bang theories don't just challenge our understanding of reality, they invite us to reimagine it entirely. So, what have we uncovered about the moments before the Big Bang? From the fascinating idea of a quantum fluctuation sparking the universe into existence to the mind-bending concept of a multiverse with endless possibilities, each theory pushes the boundaries of our understanding. The cyclical universe model suggests a never-ending dance of creation and destruction, while the holographic principle invites us to question the very nature of reality itself. These ideas aren't just abstract musings, they challenge us to rethink what we know about time, space, and existence. Yet, for all the progress we've made, the question of what happened before the Big Bang remains one of the greatest mysteries in science. It's a reminder that the universe is far more complex and wondrous than we can fully grasp. And isn't that the beauty of it? The pursuit of these answers keeps us curious, humble, and forever fascinated by the cosmos. As we wrap up, let's leave you with a thought from the legendary physicist Stephen Hawking. Look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. So, what do you think happened before the Big Bang? We'd love to hear your theories. Drop them in the comments below. And if you enjoyed this journey through the cosmos, don't forget to subscribe for more deep dives into the mysteries of the universe. Until next time, keep exploring, keep wondering, and keep looking